Hello everyone, welcome back to the NPTEL course on materials informatics. So in the last class, last lecture, we talked about linear regression as a part of classification models, and we also looked at gradient descent as an optimization algorithm, and we got introduced to a new hyperparameter learning rate, right. So in this class we will continue our discussion on classical models, and we will look at a few other models and some regularization options as well. Okay. So the next way to sort of increase complexity compared to linear regression is to actually assume that our target variable is a polynomial function, right, of the features that we have, right. So for example, if you have your target variable y varying just as a linear function of x, that is our linear regression, right. But let us say y is varying as a function of x squared, right, or a combination of x squared and x cube, for example, right. Then that is in general referred to as polynomial regression. So where your target variable can vary as some functional power, right, of your feature value, right. So basically the way polynomial regression works, right, is you add powers to your features. So this could be squaring or making your features as cubes or quadratic in nature, quadratic powers and so on, right. So you enhance the amount of powers that you have as in your feature vector itself, so that you introduce some amount of non-linearity within your features, so within your data itself, and then you fit your model through once again a simple linear regression class, right. So instead of your features being just x1, x2, x3, x4 and so on, you now have a combination of powers. So you have x1 square, x1 cube, x2 square, x2 cube, maybe x2 to the power 5 and so on, and it's the same for x3. So you have x3 square, x3 cube and so on, right. So you have not just the linear terms of your features, but you also have those powered terms of your features, right. So you now feed in this set of features, so which have both linear and non-linear terms within your linear regression class, and if you do a fit, you are basically doing polynomial regression, right. So as you can very intuitively see, this polynomial regression can have a lot of flexibility, right. So the model complexity is increasing, so you are increasing what kind of functions or what kind of dependence your target values can have on your features. So the complexity of the models are increasing, but at the same time the model is now becoming flexible. So you are not restricted to just linear powers or linear variations of your target with respect to your features. You can now have squared variation, cubic variation, or combinations of them, right. So the model can intrinsically become more flexible or more powerful, right. So to give an example of adding nonlinear data, right, in our let us say housing prices problem, right. So let us say you found median house prices to be highly correlating with median incomes, right, but maybe it is not a linear correlation, it is a squared correlation, right. Then we just square the median house price, median income feature, and then add that as an additional feature within our linear regression workflow, right. And if that gives us a better fit for the model, then yes, it is your target value, your house prices are indeed dependent on the square of the income, not just the income itself, not just a linear dependence. So how do we do polynomial regression in practice, right. So all we have to do is pre-process the features, right. So from pre-processing module within the scikit-learn package, we import polynomial features. So this is a class that can basically generate different degrees of polynomial features that you want. So let us say you want to create polynomial features of the degree 2, so you want to create squared features, right. You basically create an instance of this polynomial features class, so you say degree is 2, so you want to create squares, and since we are considering linear regression, we basically say that no, this is false. So once you create this instance of the class, you call this fit transform function, right, and pass in all the features that you have in your data set, right. So once you call this fit transform class and then pass in the features, it is going to create a new set of squared features, polynomial features, right. So you have your original set of features that is already there, and then you create on top an additional set of squared features, right. So once you create this set of squared features, you just call this linear regression model, linear regression class, and then you call this fit function, right. So in terms of doing polynomial regression, the workflow is very similar to doing linear regression. The only change is that you have to do some amount of pre-processing, right, with your features. Now polynomial regression or this pre-processing step where you create polynomial features can also be used in conjunction with other machine learning models. So polynomial regression is sort of a general or more generic term than linear regression itself. So you can create polynomial features even for a decision tree model, for example, or even for a support vector machine model, right. So this step is fairly general, this pre-processing step, but if you create polynomial features and use and you do the fit with the linear regression, then that specifically is called as polynomial regression, okay. So now that we have understood a little bit about polynomial regression, we see that polynomial regression as a machine learning tool can overfit your set of data points that you have or your data set very easily, right. So you increase the complexity of the model, typically you also increase the flexibility of the model, and the more flexible a model is, the more it can actually overfit to your data set, right. So let us take an example of this, right. So here I am plotting y versus x1. So y is once again our target, x1 is our feature, right. The blue dots are the actual data points, right. So if you look at the blue dots, they are sort of roughly roughly parabolic in nature, right. There are a few outliers, but the rough trend is it's parabolic, maybe a few deviations here and there, right. So if you now fit a simple linear regression model, that's the red line here, you see that it's not good, right. So it's not capturing your model at all, and if you use let's say x1 squared as your feature, so you do quadratic regression, which is a subset of polynomial regression, you see that it actually fits quite well, right. But if you now increase the degree that you have, so let us say you increase the degree to 300 for example, right, which is actually more than a number of data points you have, right. So the number of data points maybe it's about 50 to 60, but let us say you use a polynomial of degree 300, right, you are probably going to get a perfect or very close to a perfect fit, right, of the data points you have, but you will also see large amounts of these oscillations, right. So which implies that the model with features raised to the power 300, right, is going to be a terribly overfit model, right, to your data points that you have, right. So polynomial regression can very quickly overfit whatever distribution of data you have, right. So one sort of typical rule of thumb that we use is that if you have a degree of your data set itself, so what I mean by degree of data set is if you look at y varying as a function of x1, I see that it is roughly varying quadratically in nature, right. So I should restrict the maximum degree of polynomials that I am going to use as squared polynomials. So the maximum degree should be restricted to 2, same as or very similar to the degree of variation in your actual data set itself, right. So in other words, if your data set is not varying more than cubically in nature, does not matter whether you use a 10th degree polynomial, you are going to overfit, right. So it is important to visualize the data, understand how roughly the data is varying, and use a polynomial degree in accordance with that, right. Another important thing that we can do is ensuring that we do cross validation checks to ensure that polynomial regression models are not overfitting, right. So this is another important way to ensure that we are not overfitting our models, okay. Another sort of useful way to understand whether our model overfits or underfits is to visualize what are referred to as learning curves, right. So what do I mean by learning curve? Learning curve basically refers to how your training and validation losses or training and validation errors, right, are varying as a function of increasing your data set size, increasing your training set size, right. So this plot for example plots RMSE, so root mean squared error, which is an example of an error metric, right. as a function of training set size for a polynomial model, polynomial regression model. The red data points are training data points and the blue lines are, or blue data points are your validation errors. So these are errors on your validation set, these are errors on your training set of your data, right. So let us say you have a 10-degree polynomial model, right. So you have features up to the 10th degree polynomial that are contributing as for as features to fit your model, right. So if your degree of your data set itself, so if you have fewer than 10 data points, right, then you should be able to use a 10th degree polynomial to fit that data set perfectly, right, in some sense, right. So that is why up to from 0 to 10, so when you have fewer than 10 data points and if you are doing a 10 degree using a 10 degree polynomial, you are getting a perfect fit on your training set, right. So training set has 0 errors, but look at your validation loss, right. So our validation errors, they are very high, so, and in some cases they are even outside of this plotting graph itself, right. So the validation losses are very high, right, but as you keep increasing the training set size, right, you see that the training errors are actually increasing. So the model is not overfit anymore, it is actually fitting appropriately or it is getting better, and there is a saturation of errors close to about 60 data points or so. So beyond this the training errors do not increase significantly, which means that the model has basically learnt all that it can learn from the data that you are showing it, right. And you see that as the training errors are increasing, the validation errors are actually decreasing, right. So in other words, the model is able to make better predictions on data that it has not already seen, right. So training data points are those that it sees, validation data points are those that the model does not see, right, and the model is able to make reasonable predictions on the validation data sets. So ideally for any machine learning model you should have very similar loss or error metrics between your training and your validation sets, right. In that case the model is not getting overfit, right. If you have very large deviations between your training and validation losses or validation errors, then the model is definitely overfitting, right. So visualizing learning curves is very useful to understand when you have an overfit model or not, and it also helps us to understand what is the training set size that we typically need to ensure that our models are not overfit, right. So if you are taking a polynomial regression model with a degree 10, right, there is no point using just 10 data points or 20 data points, you probably need close to about 60 data points, right. So these are very important tools that we have to understand how well our model is doing, right. So the main takeaway message is if you have large gaps, large errors between your training and validation losses or validation errors, then your model is overfitting and it is a scenario to avoid. Okay. So now that we are talking about overfitting and underfitting of models, there is one very important trade-off that we have to understand, which is referred to as the bias-variance trade-off. So for any model we can sort of associate 3 types of errors to that model. The first one is what we refer to as bias errors. So this is due to wrong assumptions that we make in choosing our model, right. So let us say you have a target value which is varying in a quadratic fashion, so y proportional to x square, right, in your data set, you assume that y is proportional to x instead of the actual y being proportional to x square, right. In that case you have basically made a wrong assumption in your model, so it does not matter how hard you try, you are going to get a bad fit, right. And this is this type of wrong assumptions leading to large errors in the model is referred to as bias errors, right. So in general if you have lower degrees of freedom in your model, so if you have linear regression or powers of 2 for example instead of powers of 10, right, that is generally giving lower degrees of freedom, lower flexibility to that model, and those models are generally referred to as models with high biases, right. So high bias because you are making very strong assumptions about the distribution of your target values with respect to the features, right. So that is why it is called high bias, right. So bias is one type of error. The other type of error is what is referred to as variance, right. So variance is, let us say you have a general trend of your target value varying as a function of varying as a square of your feature. So y is generally proportional to x square, but let us say you have a few outliers here and there, right. The outliers could be due to several reasons. There can be just human errors, or there could be measurement errors and so on, right. So let us say you have a few outliers, and if your model becomes extremely sensitive to the presence of these outliers, right. So if you imagine that you are using a 4th degree polynomial to fit this quadratic data, right. Small changes in the outliers. So if you shift one of your data points up and down by a little bit, you will see that the sort of quadratic polynomial fluctuates more, because the model inherently has a lot of flexibility in trying to fit the data, and it will try its best to reduce the errors, right. So whenever you are shifting a data point, so you are creating a new outlier, the model will rapidly try to decrease the error associated with that outlier, right. So in other words, the model becomes very sensitive to the presence of small variations in data, right. And if you have models like that, right, then those models have high variance, right. So in general, higher degrees of freedoms that are available in a model lead to higher variance, and models that have high variance have very high chances of overfitting, right. So if you are using polynomial regression of degree 10 to fit a quadratic data, that is high variance model, and it will have errors coming because of this high variance, right. So high bias is lower degrees of freedom, high variance is high degrees of freedom, and both can lead to errors associated with your model in its predictions, right. The third one is sort of the most difficult to deal, right. So this is what is referred to as irreducible error. This comes from intrinsic noisiness of the data itself, right. Maybe the data collection mechanism is very noisy, so we are not getting as accurate a data as we want to, so those are measurement errors. Some can be human errors also, right. That could be data entry problems, copy pasting errors, right. So the data itself can be intrinsically noisy, right, and that is something that is very hard for us to eliminate completely in any given model. So we always have to assume that there is some intrinsic noise within our data on top of any bias and variance errors that we make. So the extent of bias errors we make and the extent of variance errors we make is to an extent in our control, but irreducible error may not be entirely in our control, right. Now the key thing to understand is that models that are increasing in complexity or increasing in variance will automatically have lower bias, right. So they may have higher errors because of higher variance, but they will have lower bias errors, and other way around. So if you are restricting the degrees of freedom in your model, you may have high errors due to high bias, right, and lesser errors due to high variance, right. So in other words, if you are decreasing bias errors, your variance errors are bound to increase, and vice versa. If you are decreasing your variance errors, your bias errors are bound to increase, right. So there is no way that you can actually construct a model that can simultaneously reduce both bias based errors and variance based errors. So this is a trade-off that we almost always have to understand when we build machine learning models. So we either increase the complexity or decrease the complexity. Increasing complexity leads to some kind of errors, decreasing complexity leads to other kind of errors, and we cannot create a model that can minimize both sets of errors. Okay. So now that we have understood a little bit about overfitting and the problems associated with overfitting, one systematic way to reduce the extent of overfitting of any machine learning model is to employ regularization schemes or regularization options. So what is regularization, right? So let's say you have a model with high variance, so it has a lot of complexity, so lot of degrees of freedom, lot of flexibility. You can add constraints to that model to ensure that it is not or it has a lower tendency to overfit to your data. So in other words, regularization is a way to increase bias right within your model or reduce variance within your model, right. So if you have a high complexity, highly flexible model, you try to increase its bias so that it does not overfit as easily, right. So how do you typically regularize a machine learning model? One way to do it is during training you add some kind of a penalty term to reduce the number of features or reduce number of weights and biases right, that the model uses for its fit right. So this penalty term of course will be present only during your training process. When the model is making predictions, there is no point in a penalty, right. So there won't be the presence of a penalty term when it's making predictions on a test set, but while training you can add a penalty term that adds constraints in terms of which weights and biases the model chooses to fit it, to minimize its errors, right. And this penalty term can take various forms. So you can have a ridge based penalty, a lasso based penalty, and an ElasticNet based penalty. We will cover all these three in the next few slides. Another sort of popular approach to regularize models is to do what is referred to as early stopping, right. Typically when you have very complex models such as neural networks, it may be difficult to introduce these types of penalty based regularization options. It is not impossible, it may be difficult, right. In such cases you can use early stopping as a means to ensure that the model is not overfit. So basically what you do here in early stopping is you keep tracking the error on a validation set within your training set itself. You create a separate validation set, you keep tracking your validation errors of your model until it reaches a minimum, right. So you keep varying your weights and biases of your model and keep checking your validation error or validation loss until it reaches a minimum, right. So typically if you keep varying your weights and biases and let it vary for a long period of time, you will see that the validation error will start climbing up, so it will start going up. So the minimum value is the set of weights and biases that you actually need. So that is what is referred to as early stopping, and early stopping is a very useful, very powerful technique that we typically use with neural networks. Okay, so let us understand these penalty based regularization options that we have, right. The first penalty or first type of penalty is what is referred to as ridge based penalty or commonly referred to as ridge regression also. So in ridge regression you minimize not just the mean squared error of your model, right, but you also minimize the square of the feature values themselves. This should actually read as weight values instead of feature values. So thetas are your weights basically associated with your individual features. So you not only reduce the mean square errors of your model that we reduced in our linear regression, but you also reduce the squared magnitudes right of your weights and bias terms, right. So your linear regression model has a collection of theta that you fit, right. If you have large values of theta here for each of the individual feature values, right, this will lead to a very large theta I squared term here, and the model is trying to minimize both your mean squared error and this theta I squared term, right. So it will not allow the accumulation or collection of large theta i's theta I values or large values of your weights and biases, right. So in other words, if you have too many weights and biases, right, in your model, you can try to overfit a model, right. So let us say you have 10 data points and if you have 100 features, right, if all the 100 features have non-zero weights, right, then you basically have an overfit system, right. So you can actually create several possible combinations of thetas that will give you an exact solution for the 10 data points that you have. So in other words, you are overfitting your model, right, and that is not what we want. So if you have 10 data points, ideally you should only have 10 features that are contributing to those 10 data points, right. So this ridge regression, since it has a theta I squared term in its loss function itself, so this involves a modification of the loss function during training of the model. So it not just minimizes the mean squared error, right, but it also minimizes the number of actual features that get a significant weight associated with them, right. So it is reducing the tendency of the model to overfit, right. So that is ridge regression. In the case of Lasso, so Lasso basically has an expansion, it is called least absolute shrinkage and selection operator. So in the case of Lasso, instead of minimizing the squared values of theta I, you now minimize the mod of theta I here, right. So otherwise there is no difference. So this is minimizing sort of Euclidean values and this is minimizing Manhattan values, right, of your theta as a vector, right. So of course since you are modifying your loss function here which is your j of theta here by adding these penalty terms you now have an additional hyperparameter which is your alpha, right. So the alpha is basically determining what is the trade-off that you have between your bias and variance, right. So if you have very high values of alpha you are adding in a lot of constraints to the model, so increasing the bias, right. If you have very low values of alpha then you are providing a lot of flexibility to the model, right, and hence you are increasing the variance, right. So if you have high values of alpha for example here, right, even smaller values of theta square will push up will increase the value of this loss function. So your algorithm will try to minimize the number of non-zero weights that you have, right. So in other words the model will increase the bias, right. If you have low values of alpha, so or if you have alpha equals 0 for example, right, then you are only trying to minimize your mean squared error, so you are not adding any bias to your model, in other words you are increasing the variance, right. So this is where the bias variance trade-off comes in. So hyperparameter alpha basically acts as the balance between the two. So let's look at some visual examples, right, of how ridge and lasso work in practice, right. So I am once again plotting some a target value y as a function of your feature values x here. The blue dots represent the collection of data points, right. So if you do not regularize your model at all, so if you use alpha equals 0, you see that the left plot is for ridge regression, the right plot is for lasso. Both ridge and lasso give rise to the same sort of curves, right, which makes sense because your alpha is 0, so it does not matter whether you are taking in Euclidean distances or Manhattan distances, you are going to get the same fit. So alpha equals 0 basically represents a simple polynomial fit, polynomial regression, right. If you take higher values of alpha, so alpha equals 1 is a fairly large value, right, you see that ridge regression is predominantly linear here with some minor non-linear behavior here, right, whereas lasso is completely flat, it is just linear regression here, right. So it is assuming that y is almost a constant with respect to x1, so as x1 varies the target value does not vary at all, right. So it almost assumes that y is a constant. So what this indicates is that in general lasso creates sparser models than ridge regression. So lasso is very good at eliminating non-important features that you have in your data set, right, and it is very quick and powerful at doing that too compared to your ridge regression, right. So you can also see that if you have two if you have a fit of ridge regression at alpha equals 1e to the power negative 5, you see this green curve here, right, and you see that lasso which sort of achieves a similar behavior to this ridge regression gets this similar behavior even at lower values of alpha, right. So even at lower values of bias variance trade-off, since lasso is a very has a very strong inbuilt bias to it, even at low values of alpha it will give you sparser fits compared to your ridge regression, right. So the optimal alpha may be different for your ridge regression compared to your lasso, so that is something to keep in mind. Since lasso by itself creates very high bias in your model, it eliminates non-important features very quickly, it can have convergence difficulties compared to ridge regression. We can also visualize these convergence difficulties. So for example I am plotting how models generally tend to minimize their errors. So for example in this plot, so I am plotting two different features here, so theta 2 and theta 1, right. The heat maps basically correspond to the values of identical loss functions in the top panel for lasso, so these two panels are for lasso and these two panels are for ridge regression. The yellow lines basically indicate how a linear standard linear regression would actually evolve, right, under these loss functions, right. So if you look at lasso you see that, so and the red dot basically indicates your optimal set of weights weight terms that you should reach for minimizing your error, right. So if you look at lasso, right, so you see that the model quickly approaches close to the minimum, but then it sort of oscillates quite a lot around the minimum, right. So lasso can create sparser models very quickly, but it can have convergence difficulties while trying to reach the best possible fit, best possible model. Whereas ridge sort of arrives at the minimum more slowly, but it has a more smoother trajectory. So it arrives at the minimum in an almost unrestricted fashion, right. So almost always Ridge gives you slightly more stable models compared to Lasso, but Lasso gives you really sparse models. So if you really want to understand which are the most important features or which are the minimal set of features that really govern your target variable, you should go for Lasso. But if you want sort of more robust, slightly more stable models which may take a lot of effort to fit, may take more time to fit, then you should go for ridge regression models. And another final point to note, since you use Euclidean in Lasso you use Manhattan distances, right, amongst your features in your cost function, in your error function. That's why you get these kind of rhombus like shapes here, whereas in ridge regression you use Euclidean distances or typical distances that we think of in terms of Euclidean space, 3-dimensional space. That's why you get squares here, right. So points along the square all have the same radius in some sense, points along the rhombus have the same moduli of distance, so they have the same Manhattan distance, right. So that's why these heat maps appear as rhombus like, and here the heat maps appear more circle like. Okay. Now what is ElasticNet, right? So ElasticNet is another way to add a penalty as a regularization option, and it offers you some kind of a middle ground between your ridge regression and your Lasso regression, right. So basically in ElasticNet you modify your loss function to include your mean squared error, and both your Lasso error term, which is your Manhattan distance, and your ridge error term, which is your Euclidean distance, right. So you now have alpha. So alpha is the existing hyperparameter that we had already in our ridge and Lasso regressions. You introduce a new hyperparameter called R. R1 is referred to as the L1 ratio, right. So R determines the trade-off between your Lasso error and your ridge error basically. So ElasticNet gives you an additional hyperparameter that lets you tune between how much of Lasso like behavior you want to have in your model or how much of ridge like behavior you want to have in your model, right. All of these ridge, Lasso and ElasticNets they all have dedicated classes. So if you want to implement them, you can sort of import those classes from scikit-learn.linear model module, and once you have imported, you can just simply perform linear or polynomial regression on top. Another sort of nice way to use these regularization options is to simply use this stochastic gradient descent regressor class. So remember that SGD regressor has options to do batch, stochastic as well as mini batch type of gradient descent. So it has all three options. So in addition it has a penalty keyword or penalty argument which you can define it as either L1, L2 or ElasticNet. So L1 refers to Lasso, L2 refers to ridge, and ElasticNet refers to ElasticNet. And for ElasticNet you will have an additional keyword or argument called L1 ratio, right. So for L1 or L2 you will only include the alpha, for ElasticNet you would also need to include the L1 ratio, which is your R term here. Okay, so that is adding a penalty. The other approach to sort of regularizing a model is to do early stopping, right. So as I had mentioned before, so in early stopping we track the loss function, the root mean squared error for example, as a function of some parameters, some combination of weights and biases. So in typical complex models we will track these losses as a function of epochs, because epochs refers to how many iterations you are actually performing on the model. So each epoch corresponds to m number of iterations, where m is your dataset size, right. So the more number of epochs you are having, the more modifications you are making to your weights and bias terms, right. So you would see that your loss function, your root mean squared error is varying both for your training and your validation sets. For training it keeps decreasing as you keep increasing your number of epochs. So as you keep increasing your weights and bias terms, for a very complex model you will see that the model gradually starts overfitting on your training set. So which implies on your validation set the losses hit a minimum at some point, and then as the model starts overfitting, you see that the losses start increasing on the validation set, right. So the best model that we need is actually at this epoch. So let us say this is about 250 epochs, and we should get the weights and biases of the model at this epoch to ensure that we are not overfitting our model, right. And this can be used within even our stochastic gradient descent regressor class with an option called warm start, right. So if you do warm start, you can basically say that at this epoch you start the model with in its prediction mode at this set of epochs, so at this set of weights and biases. So there are options to do it in scikit-learn, and we will explore early stopping or we will use early stopping quite regularly when we are dealing with neural networks a little later in the course. But early stopping is a very important regularization criterion that is a must to use for highly complex models. Okay. So with that I will summarize today's lecture. So we looked at both linear and polynomial regressions. So in this specific lecture itself, we looked at more polynomial regressions and how bias and weight terms contribute to both of these ways to do regression. We did look at gradient descent as an algorithm. It is particularly useful for handling large data sets. Hyperparameters that are associated with gradient descent are learning rate, very important hyperparameter, number of epochs or tolerance, one of them is typically used, and also batch size. This is more important when you use, let us say, mini-batch gradient descent. So what is the subset of training data points you want to calculate the gradient on, right, when you are updating your model from the first step to the second step or the second step to the third step, right. So batch size is another important hyperparameter that comes up quite regularly as you keep increasing your model complexity. We also understood a little bit on bias variance tradeoff. So models that have high biases will have high errors coming from that high bias, and models that have high variance will have high errors coming from that high variance, and both bias and variance are determined by the amount of complexity that that model has inbuilt, right. And we also looked at learning curves to understand the tendency of models to overfit and what corresponds to a overfit model versus what corresponds to a optimally fit model. We also looked at some regularization options including rich, Lasso, ElasticNet and early stopping. We are not done yet with our classical models, so in our next lecture we will look at other classical models starting from logistic regression, then we will do softmax regression, k nearest neighbors, and then support vector machines. So with that, thanks once again for joining today. I will see you all in the next lecture.